Okay, today we are going to graph logarithms. So to graph a logarithm, we have to understand how is that related to our exponential functions because we actually graphed exponential functions already. So graphs of logarithmic functions are basically the inverse of an exponential function. So if you remember what an inverse is, that's when you're switching your x and y values. So let's start off with a logarithmic function. Y equals log base b of x. Okay, y equals log base b of x. Now, if you remember, when we found the inverse, we actually had to switch the x and y, and we solved for y. So what I'm going to go ahead and do is I'm going to take this function, and I'm going to go ahead and switch the x and y first. So switching it, I have x equals log base b, and then the x is going to become the y. So that's just switching the x and y. Now we have to solve for y. Now, when you solve for y, we actually don't know how to get rid of the log just yet. So what we're going to do instead is just rewrite, because yesterday we transformed exponential to logarithmic and logarithmic to exponential. And so we're going to take this, and this is in logarithmic form, and we're going to write it in exponential form. Now, when we did it yesterday, it didn't quite look like this. Most of the problems were log base b of some number equals another number. So remember when you did the hook, we started with b. We said b to the x equals y. B to the x equals y. So that's what I'm going to write in this exponential box. B to the x. And instead of writing equals y on this side, I'm going to go ahead and write y on this side. Now remember, these are not the same thing. These are inverses of each other. And we graphed exponential functions. We actually graphed exponential functions that were in the form of a times b to the x minus h plus k. So we are going to be shifting here, but we are going to first practice what is the inverse of the function. Now, you can take all these logarithmic forms, switch x and y, and then rewrite it in exponential form. But if you can see the shortcut between log base b of x and b to the x, this will be much easier than rewriting it every single time. So here's your log. See that b? That's your base, and that's your exponent when you write the inverse. So let's use the shortcut here. So this is y equals log base 4 of x. So what's the b? The b is the 4, and then the x is going to be the exponent. So the inverse is just simply y equals 4 to the x. All right, now this is in exponential form, this form. Now we're going to write the inverse, which is going to be in logarithmic form. So we have y equals log. What's the base? The base here is 6 of x. Remember that when you write in logarithmic form, nothing is in the exponent. So this is all one line. The 6 is just the one that's dropped down, just like this is. All right, let's go ahead and go to this one. So this is logarithmic form. So the inverse is exponential. And so it's the base of 1/3 raised to the x power. All right, now this one's a little tricky because it's e. Do you remember that the inverse of e is ln? So the inverse is just y. And if you wrote log base b of x, that is the same thing as ln of x, but you must write ln instead of log base e. Okay, it must be ln x. And then this last one says ln x is our function, so the inverse of that is simply e. Y equals e to the x. Okay, we're going to be graphing these logarithmic logarithms. And if you take a look at this, there's our a. That changes it. Either if it's negative, it has a reflection, or there's a vertical stretch or compression. Then we have our x with inside the parentheses with the x is your change moving it left or right but opposite, and then k moves it up and down. You should be very familiar with that. So what we're going to do is we're going to change the table. Now remember that the logarithm, we're going to use the fact that these are written in logarithmic form, and we're going to make a table of values, and it's easier to use exponential to figure out the values in the table. And I'll show you what that means in a minute. So we're going to describe the transformations and graph it, keeping in mind that we're going to have a table of values for each of these because the base is different for all. That has a base of 3, base of 2, base of 4, and ln has a base of e. All right, let's start with this first one. So we're going to go ahead and create the parent function. And remember, parent functions simply get rid of the a, the h, and the k. It's just going to be log base 3 of x. We're getting rid of the h and the k. Okay? So y equals log base 3 of x. That's our parent function. And we're going to be using this right here to help us fill out a table. Now I'm going to go ahead and rewrite this in exponential form to help us solve. So this is base 3 to the y equals x. Okay, I'll rewrite that. 3 to the y equals x. This is not the inverse. This is simply just rewriting it in exponential form. 3 to the y equals x. And now I'm going to create my table of values, but remember that it's easier to solve 3 to a power. So we usually always wrote negative 2 to 2 on the x side. But since it's the inverse, I'm going to go ahead and write negative 2 to 2 on the y side. And the reason for that is because I am going to plug these values in for that exponent. Notice it's easier to say 3 to the negative 2 power opposed to saying plugging in a value for x and say 3 to what power is that x. Okay. All right, so let's plug this in. We're going to do the mental math. 3 to the negative 2 exponent. Remember, negative exponent flips it. So let's go ahead and do 3 squared first. 3 squared is 9, and then the negative flips it. 1 over 9. If you're really bad with negative exponents, start with a positive. Say 3 squared. 3 squared is 9, and the negative here would be in the exponent, which flips it. So you could just do that. 3 to the first is 3. The negative 1 will flip it. And anything to 0 power is 1. So this is our table of values. All right, now we're going to go ahead and look at our transformations. So remember here we have a positive 4 and a positive 1. But when we write the transformations, it's opposite same. So opposite of positive 4 is negative 4. And so we're going to go negative 4, which means left 4. And the plus 1 makes it go up 1. All right, we're going to go left 4 and up 1. Now I'm going to put my open circle. Do not draw your horizontal asymptote. Remember that this is an inverse of an exponential. Exponentials had a horizontal asymptote, but if you were to change the horizontal asymptote because it's reflected over the y equals x axis, it's actually now going to be a vertical asymptote. I know that's really tricky, but instead of horizontals for exponential, this is the inverse, so we're going to look at it going up and down. So we're going to draw a dashed line up and down. Remember, that point is not part of the graph. That's just a reference point for us to plot the rest of our points. Okay. Now, keeping in mind, since this goes up and down, the equation of a vertical line is x equals, and x happens to equal negative 4 in this line. All right, let's go ahead and take the points here and graph it here. We'll pretend that that is 0, 0. So this is going to be a little tricky at first, but let's go ahead and plot the points. So from here, we're going to go right 1/9. So it's just hardly anything. And then we're going to go down 2. All All right, go back to this reference point. Go right 1/3 and then down 1. Then we're going to go right 1, and we're not going to go up or down. Then we're going to go 3, 1, 2, 3, and then 1. And then last one is 9. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, and then up 2. So these are the points that we're going to use to draw. Keep in mind that an asymptote is a line that a graph gets closer and closer to. So this graph is going to get closer and closer to this asymptote, keeping in mind that it will not ever touch that asymptote. Make sure there's arrows on the end to denote that it goes on and on forever. So this graph looks quite a bit different from your exponential, but if you kind of imagine, and I know this is not really it's not turning, it's not a rotation, but exponentials really look like that. And if you reflect it across the y equals x axis, that's when it turns into this. All right, let's go ahead and write the domain and range. All right, you can write the domain and range however you want. I'm going to go ahead and write it in interval notation. Okay, so the domain, we're looking at the graph. Does this graph go to the left and to the right? So it doesn't go to the left completely. It definitely goes to the right. It actually starts before this -4, before it goes to the right. So it's going to start at -4, but it doesn't include -4 because it never touches a line. And it goes on and on forever to the right. So that's infinity. And the range now, does this graph go up and down? Yes, this graph keeps going down. It's slowly going up, but it is going up. So this is going to be just all real numbers, which is -infinity to +infinity. All right, let's try the next one. So in the next one, we have a 1/2 in front of there. So that's going to change the y values of our table. But we're going to first start off with writing the parent function. So getting rid of the a, the h, and k, so basically getting rid of that and this, that's our function, log base 2 of x. Y equals log base 2 of x. Now I'm going to rewrite that in exponential form so that it's easier to plug in. So this is going to have a base of 2. 2 to the y equals x. All right. When we make our table of values, we want to write -2 to 2 on the y side, so it's easier to plug in. Okay, 2 squared, that's just 4. A negative exponent flips it, 1/4. 2 to the first is 2, negative exponent flips it. And anything to the 0 power is 1, so that's our table of values. All right, we're ready to look at our transformations. All right, it has a 1/2 there. So what does a 1/2 do? It is a vertical compression by a factor of 1/2. This right here is going to make it go opposite. So thinking of +1 instead, right 1. All right, so I'm going to go ahead and just go right 1. And that's going to be my reference point. Remember that it is a vertical asymptote. You can even think of logarithms. All of these are logarithms, and it has the letter L. So maybe you can think of this as your asymptote. All of these have a vertical asymptote with the L. Okay, equation of this line is an x equals 1. And now we're going to plot all these points from this reference point. Pretend that's like your 0, 0. So we're going to go right 1/4, which is hardly anything, and then down 2. Oops, I forgot the 1/2, sorry. So let me go ahead and change these values. Remember that an a value changes all of the y values. I know I mentioned it earlier. And we're going to multiply all of these by 1/2. We always multiply it by whatever the a is. And a happens to be +1/2. So let's redo this again. So we're going to go right 1/4, but we're going to go down, not -2, Half of 2 is 1, so we're actually going to go down only -1. All right, and then we're going to go 1/2 to the right, and then half of -1 is -1/2. And then we're going to go right 1, and 0 times anything is basically, it's going to be 0. So right 1, and it's not going to go up or down. We're going to go right 2, and 1 times 1/2 is +1/2. And then 4, 1, 2, 3, 4, and instead of up 2, half of 2 is up 1. Okay, so the domain. This graph does not go left and right. It actually starts at 1 before it goes to the right. It does not include 1, so it's a parenthesis. This does go up and down, so it goes from -infinity to +infinity. Okay, let's go ahead and go to the next one. So the parent function here, get rid of the a, get rid of the h and k, log base 4 of x. All right, let's write this in exponential form. So the base is 4. 4 to the y equals x. Make sure you write your -2 to 2 on the y side. All right, now let's plug it in. 4 squared is 16. Flip it, 1/16. 4 to the first is 4. Flip it, 1/4. Anything to 0 power is 1. Okay, transformations. What does the negative do? A negative basically is going to reflect in the x-axis. And then the -3 makes it go down 3. All right, so I'm going to start down 3. Open circle, vertical line. That equation is x equals 0. All right, now when I plot these points, keep in mind that I had an a value of -1. So I'm basically going to take all these values and multiply them all by -1. So it basically changes all the signs. So start at your reference point, go right 1/6, and then instead of -2, because -2 times -1 is +2, so it's going to go up 2. So right 1/4, and then -1 times -1 is +1. All right, then 1 and 0 times anything is 0. Then we're going to go 4, 1, 2, 3, 4, and we're going to go 1 times -1, which is -1, so it's going to go down 1. And then 16, 2 is way off my graph. So this graph reflected, so it's going to be a graph that's kind of upside. So when you think of a reflection in the x-axis, think of the x-axis this way. We always actually reflect first before we shift things left, right, up, and down. So originally, these logarithms always kind of hook over to the right here. So when you flip it from here, that hook is actually on the bottom, and this tail bottom goes up to the top. So that's what it looks like whenever it's reflected. We are never doing any reflections across the y-axis. So the graph will never go from this side over to this side because we're not doing reflections across the y. Okay? At least in this class. We will do it in pre-cal. All right, so let's take a look at the domain and the range. So thinking of the domain, this graph still does not go left and right. It is still to the right of this asymptote. So it's going to start at 0 before it goes on to the right. It actually doesn't touch 0. It just gets really close to it. And then the range, it does go up and down. So that's all real numbers from -infinity to +infinity. All right, and then the last one is ln. Keeping in mind that ln is the same thing as a log base e. So let's go ahead and write the parent function, which is just getting rid of the 3 and the -4, which is ln of x. All right, let's rewrite that in exponential form. So this is e for the base to the y power is going to equal x. Now we're going to write the -2 to -1 on the y side. And I don't know if you remember, but you had to memorize E in the table for E. So it's just switch. So if you remember your values, it's 0.1, 0.4, 1, 2.7, and then 7.4. And you'll have to memorize this again and refresh yourself for the test for this unit. Okay, transformations. There is a 3 in the front, so that's going to have a vertical stretch by 3. This -4 is making think of opposite, so it's going to go right 4. All right, so the equation of the asymptote. Well, if we start at right 4 and draw this dashed line, that's going to be x equals 4. All right, let's plot these points, keeping in mind that since we do have an a value of 3, all these y values are going to be multiplied by 3 when we plot the points. All right, so let's start off at our reference point. We're going to go over 0.1, which is hardly anything to the right, and then -2 times 3 is -6. So we're going to go down 6. 1, 2, 3, 4, 5, and 6. All right, now we're going to go 0.4, which is almost a half, and then -1 times 3 is -3. 1, 2, and 3. All right, 1 and then 0 times 3, which is 0. Then we're going to go 1, 2.7, and then 1 times 3 is +3. 1, 2, 3. All right, so these points are all the ones I'm going to use because the 7.4 is definitely off my graph. So I'm going to go ahead and draw this in, keeping in mind that this does get closer and closer to the asymptote still. And this just kind of still hooks over this way. Okay, the domain. So looking at the domain, this is still on the right side of this asymptote. So the right side means it's going from 4 to +infinity, and the range, yeah, it goes up and down, -infinity to +infinity. All right, so all of this is the graphing of your logarithmic functions. Now we get to do our word problem, your favorite. All right, in order to do this, you are going to need a graphing calculator to have it come up with the equation, because we're going to have to do that again. But before we do that, let's go ahead and read this. So during the period between 2001 and 2011, the average price for an ounce of gold doubled every 4 years. In 2001, the average price of gold was about $270 per ounce. So I'm just going to do a little refresher. If you don't remember, our formula for exponential is y equals a times b to the x. And the a is basically representative of your initial amount, or what you begin with, whereas the b is your rate. Now, when we were using this equation, we had to do 1 plus r or 1 minus r, but once you simplified it, that is your b. Now, in this case, it didn't give us the rate in a percentage. They just said it doubled every 4 years. So we're going to have to make that representative in the equation. So let's start off with our function model here. We're writing an exponential function for the average price of an ounce of gold as a function of time in years since 2001. Give me 1 second here. Okay, so let's write this exponential model for the average price of an ounce of gold as a function of time in years since 2001. So here's what the exponential model should look like. So here we have y equals, and then what is the value that you begin with? Well, in the year 2001, the price of the gold was about $270 per ounce. So the initial value is 270, and here's the part that gets a little tricky. So it's doubling every 4 years. doubling every 4 years. So double means 2. You're multiplying by 2 every single time. That's your rate. It's doubling every time. And here's where it gets tricky. It doubles not every year, it's every 4 years. So if it's doubling every 4 years, you cannot just put t, because it doubles every 4 years. So you have to do 1 over 4 times t. Now, I know some of you might be thinking, every 4 years, why isn't it 4t? But remember that when does it actually double? After the 4th year. So think about, if I plug in the number 4 here, if I plug in the number 4 for the t, 1/4 times 4 is 1. So then the double only happens once. If you wrote 4t, then in 1 year it would have doubled 4 times. That's not what we want. We don't want it to double 4 times in 1 year. We want it to double every 4 years. So that's why it's 1/4 t. All right, so this is the model function. And now what we're going to do is we're going to write, so this is using our exponential function here. But you also have the way you can do this is using your graphing calculator and using the stat part of it. So I'm going to review that when you use your graphing calculator and you have it actually do the regression. All right, so first of all, we're going to take a look at our years here, and we are not putting in the years. Remember, you don't want to put 2001, 2002. Our initial year is 2001, so this year should be at 0. You only change it when it's years. If these are values that went centimeters or grams, you do not want to change the values. But these are years since 2001. So 1 year past 2001, 2 years past 2001, 3 years past. Okay. And then what we're going to do is we're going to plug this into the calculator. Okay, so what we're going to do is we're going to use our graphing calculator. And if you don't remember how to get to the table, you hit stat. So stat is this button right here. And then you want to go to edit, number 1, or press enter. Now if you have something here, don't forget to arrow up to the top, press clear, and then enter, and it'll all go away. All right, I'm going to go ahead and put these values in. And then you want to go to line 2 and put these values in. Once you have it all in, then you want to go ahead and hit the stat button again for it to calculate. So arrow over to calculate, and we want the exponential function. So it's 0 or arrow down and then select exponential. Go ahead and go down to calculate, and then here's the equation. Notice that the a value is different from the a value that we came up with, because this is using the value that is from our information, whereas this is using the best fit. So I'm going to plug in these values into this function. So we have y equals 251.82, and then our b is 1.19 raised to the x power, or you can write t. Okay. Now this is using just the graphing calculator and the table. So this is just another way of writing the equation. but both are made a little differently. Okay, this next part is quite a bit challenging for some of you to understand, so you may have to rewind and watch it a couple of times in case you really are having trouble. So what we're going to do is we're going to find the inverse of the exponential model after rewriting it with a base of e. So we are going to write the inverse of the exponential model. But we have to first rewrite it with a base of e. So this right here is not written with a base of e. So I am going to change it to have a base of e. Now we did exponential growth and decay rates before. So remember that we don't look at the a and we don't look at the variable here, t or x. We're really looking in between here, and that really is your exponential growth rate or decay. So I'm going to be using this value right here. So really what we want at the very end, if we want it to have a base of e, is to look like this. Y equals a, and then we want e as the base, right, base e, to the c power of some sort, and then the t. Okay, so really this is the part that we really need to find. We have the a, and we need to change the value 2 to the 1/4 to be e to the c, because the a and the t are right there. So we're just looking at this middle. So this middle is 2 to the 1/4 power. We have to change this to actually be e to the c. So we're going to go ahead and make that equal e to the c. Okay, this right here. Now, this right here, if you're doing the homework online, they want you to actually take this and get the value. So let's go ahead and do that first. So I'm going to get out of this. There's a little bit of a reflection there. Maybe I'll go here. Okay, so now I'm going to go ahead and go 2 raised to the 1/4 power. Okay, and that is approximately 1.19. Okay, the further out you go is better, but 1.19. So 1.19 is approximately what e to the c is. Now remember, e is not a variable. E is a number. That's the 2.7. We have to solve for what that c should be, because all we're going to do is plug in the a and the c, and then this equation will be an exponential model with a base of e. So how do you get that c to come down so it equals? What we're going to do is we're going to rewrite it. This is in exponential form. We're going to rewrite it in logarithmic form. Now, when I rewrite this in logarithmic form, it's going to be log base e. But do you remember that log base e is actually ln? Log with a little base of e is ln. So ln, so it's like thinking of it as like a little e here. E to e is the e is the base. The exponent is what a logarithm equals. So this 1.19 is here, and that's what is going to equal c. So ln of 1.19 equals c is exactly the same thing as 1.19 is about, well, I guess I should write about e to the c. It's just written in another form, logarithmic form. All right, we're going to plug this into the calculator. So let's see if I can get this to show up again. So I'm going to go ln of 1.19, and this is going to be about 0.174. 0.174. Okay, so we finally have c. So we're just basically going to rewrite this equation here and just replace the c with this. Okay, we're going to use this equation here, replace the c with this, and also the a which we know from the previous section was 270. We're just rewriting the 2 to the 1/4 to be e to this power c. So that's going to look like this. Y equals 270, that's your a. We're changing this to have a base of e, raised to the c power, and the c is 0.174, and then you have your t. Okay, so that's rewriting it in that form. But we're not done because that's not the answer. I know that was a lot of work, but we're going to find the inverse of this exponential model. So to find the inverse, what we're going to do is we're going to basically get the t by itself. Okay? So to get t by itself, we're going to have to strip everything else away. So to get rid of the 270, I'm going to have to first divide by 270. So that cancels. So we're left with y divided by 270 equals e to the 0.174t. Again, we want that exponent to drop down, so we're going to rewrite this whole thing in logarithmic form. All right, let's see if you remember how we did that. So e in logarithmic form is ln. So we're doing ln of this number, y divided by 270, and then it's going to equal the exponent, which is this, 0.174t. Remember when we did the hook, there's the base of e. E to this exponent equals this. E to this exponent equals this. And that's what's here. E to that exponent is this. All right, now we're not done yet because we still have to get t by itself. And so if you notice here, we still have to get rid of this. So in order to do that, we're going to divide 0.174 to both sides. So now we have t by itself finally. Now the only thing, though, is that for this, we don't usually write the fraction with the decimal all together. So what I'm going to do is I'm actually going to take this value. Notice it's in the denominator. So it's really 1 over this number. If I were to rewrite this, that's actually 1 over this number. So I'm going to find out what that value is. Okay, so here we go. I'm going to do 1 divided by the 0.174, and that's going to get me about 5.747. Okay, so we're going to go ahead and plug that in. T equals 5.747 ln of y over 270. Okay. All right, and then the last part is performing the logarithmic regression on this table. So this is actually exponential here, and this is a logarithmic here that we're looking at, and logarithmic is also found in the stat part of your calculator. So performing the logarithmic regression on this table of values, we are going to let me get this to not be glary. Okay, I think I got this to be not as glary. Okay, so what we're going to do is we're going to let the calculator figure this out. Now we're going to do a logarithmic regression, so it's going to be a natural log because we don't want to just pick any base, so it's going to be a natural log we're going to be using. Now when we go into our stat table, we had 0 through 10 as your X value and then your average price as your Y values. When we do the logarithm, remember when we graphed earlier, we want these switched. So since these are supposed to be switched, you could do one of two things. You can go into stat, go to edit, and re-put in all those values in the right column, putting all of these over here and these over here. But that's a lot of work. So instead, what we're going to do is we're going to go to stat, and when you go to calculate the natural log regression, which is number 9, we're actually going to just switch it here. We don't want the X values to be list 1. We want that to be list 2. So to do that, on the very bottom, you notice it has L1, L2. You'll have to hit the shift button or second button and then hit L2. What'll happen is L2 will change to be the X. Then arrow down and we're going to change that to be L1. So how do you change that to L1? We go back to the bottom, hit the second button, and then hit the number 1, which is L1. And now notice that my actual equation here is now going to be found by using my X values from list 2 and my Y values from the list 1. So go ahead and go down to calculate. And here we have our our logarithmic regression. So we're going to plug in those values. It's y equals, and then you have negative 31.293, and then plus 5.6. And since usually I would do 3 decimal places, past the 9 is a 6. So that moves the 9 to be a 0 and the 6 to be a 7. And then ln x. Okay. All right, so comparing this with the inverse model from part B, which is this right here, you can graph these both into the graphing calculator to see how close they are to each other. Okay, so let's see, we have 5.747 ln of y divided by, which y is going to be x, divided by 270. And we're going to compare that to negative 31.293 plus 5.670 ln of x. And do we want to let's go ahead and zoom fit. Zoom start. Oops, wrong one that I pressed. Zoom fit. So there's one graph and there's the other graph. And they are pretty close to each other. Not exactly on top, but they're pretty comparable. This is obviously doing it by hand, and this one is doing this using the graphing calculator. Okay? All right, so don't forget you have 2 parts to your work. Number 1 is the half worksheet, and the second one is the interactive. And all of this will be due when I see you again on Monday. Have a great weekend. Before I let you go, sorry if you already clicked off, but maybe you'll go back on and see that there's still more to the video. There is one problem on the homework online where it gives you a coordinate, let's say like this, and they have an arrow so that it tells you how do you move this, and they'll have a box and then whatever numbers here. So these were already going to be written in this form, and then they have a box here to fill in. So all they really want you to do is, this is like your x here, and this is like your y. So what's your x? 1. What's your y? 4. And then you simplify it. 1 plus 2 is 3, and 4 times 2 is 8, and 8 minus 3 is 5. So that would have been just the answer online. So just in case you need a little additional hint for that. Okay, now have a great weekend. Bye.